All right, welcome back. So we're working on this railing thing that's made out of splines. And in this video, we're going to dive into, right now the railing's just kind of sitting on the ground, and we're going to dive into how to give it some supports, give it some height. And we're going to do that using some C++. As I mentioned in the last video, that's not strictly necessary. Not going to be using any C++ only APIs or anything like that. I just kind of prefer C++ when I'm getting really nitty gritty with my hands dirty and like math and stuff like that. But all of this should be doable from blueprints or Python if you prefer. So let's get started. So I'm going to go to my content browser and I'm going to go to my C++ classes and I'm going to create a new C++ class. And this is just going to be some functions that I want to be able to call from blueprints. So I'm going to create a blueprint function library and I'll just call it like geometry helpers. And we'll hit create. So my editor crashed while I was doing that. So I had to rebuild the spline real quick, but it's no big deal. So I got my blueprint function library right here. And that's good. We're going to dive into that in a second. But first, I just want to talk about what the heck we're going to do once we get there. So we have this spline, and this is what I want the interface to be for the user of this thing. I want them to just be able to drag these points around and do whatever they want to make this railing whatever shape they want. We need to add the actual railing shape. So this is going to be like the top of the railing, but we need to add like, the legs, like the poles on either side so that it's standing up. And so what we're going to do is we're basically going to create another spline that is based off of this one. It's kind of a copy of this one, except we are going to add some extra control points on either side that are going to be those supports, and is going to be the rounded corners that I've been talking about and stuff. So we're essentially going to have two splines. One of them is for the user to author the shape of the railing with, and then the other one's going to be the thing that we're actually going to use for the sweep. So we need to go in here, we need to create another spline, and I'll just do that, and I'm going to name this one differently. I'm going to name this helper spline. This is the spline that we're actually going to use for the sweep once we copy the data over from the original spline and add our own control points. So the code for copying over the control points from the original spline into our helper spline and adding the extra control points at the end and stuff, that's going to be what's going to happen in C++. So let's jump over to our C++ blueprint function library, and I'm just going to define an API. I don't actually have a good name for this function at all, but it's going to be something like, it's going to return a spline component, and sure, we'll call it create offsetted spline. I know that's not a word, but we're gonna take in a source spline and a destination spline and a vector, and that's going to be our operation here. We're going to kind of copy the points over from the source spline into the destination spline, but as we do so, we're going to offset them by the vector, and we're going to write to the destination spline. We're also just going to return the destination spline as a convenience so that this is easier to use from blueprints. So this is going to take in a spline component dest. Sorry if I get any unrealisms wrong here. I'm still getting used to the capitalization and stuff. The source is going to be another spline component. It's going to be const because we don't need to modify it. And then the offset is just going to be an f vector. And this function needs to be callable from blueprints, obviously. So it needs to be a U function that's blueprint callable. All right, let's implement it. So over in my CPP file, I'm going to start spamming this out. My IDE is hopefully going to step in and help me. There we go. So first thing we need to do, because this is callable from blueprints, is very not only possible, but likely that these will be null. So we need to make sure that we check that stuff so that we don't crash our entire editor by calling these functions. So if dest is not valid, we're just gonna return dest. We We could return null or something, but might as well just return dest. And then if source is not valid, I'm doing these separately for a reason that we'll see. I could have just done or, but I'm writing them out as separate blocks, as we'll see in a moment. If source is not valid, then return dest. Or if we're gonna get the number of control points, so that's going to be count, and that's going to be source get number of spline points. And if count is 0, then our algorithm's not going to work very well. So we're just going to return in that case too. In any other case, well, we're going to return dest ultimately anyway, so we can just do that. But these kind of early out clauses are to protect us later on, so we can just assume that these things hold later on in the code. So another thing that I want to do in between, and this is why I wrote these separately, is that if we have a valid dest, we always want to clear it out, because there might be data in it from the last time it was passed into this function, and this function should have the effect of resetting it, regardless of whether the source is valid or not. We want that to we want this function to always kind of wipe the slate clean at least. So right here, I'm going to say dest clear spline points, and that's just going to happen regardless of whether we have a source to copy from, just so that this function's behavior is nice and predictable. Okay, so now let's actually just look at the API that we're going to be using here. So dest is empty now because we cleared spline points, so we know that. And we know that we have a valid source to read from. So the method that we're going to be using on dest in order to add a point is called add point. And it takes in this fSpline point struct. And this is just a big bundle of data. It has a location, it has a scale, it has some tangents, it has a rotation, just describing the point thoroughly. And we can pass that in. We can pass one in to add 1 point. We can pass a bunch in at once to add a bunch of points. But something interesting about this API is that once you've passed these fSpline points in, they kind of dissolve, and there's no way to get them back out. So if I add an fSpline point, and then I want to say, hey, what was the fSpline point that I just gave you? There isn't really an API for that. I can say, hey, what's the position that I just gave you? What's the rotation that I just gave you? What's the tangent that I just gave you? But I can't grab the entire struct back out. And I believe that's because internally the spline is actually not storing those structs. It's kind of splitting them apart, storing them in parallel, separate data structures for performance reasons. And so if we want to actually piece back together an fSpline point so that we can, say, copy it from one spline to another, we need to write a little bit of logic to do that for us. It's very simple, but it's just a little bit of work. So I'm going to write a little helper function here, and it's going to help us extract some spline point data from each index. So that's exactly what I'm going to call it. It's going to be static because it's not needed outside of this translation unit, and it's going to be extract point at index. I like the name extract for this because we're like reaching in, we're grabbing some information that's available to us, but it wasn't like readily available to us. So we're kind of getting our hands dirty. We're a little extraction team. But yeah, we're going to be looking into this spline, and we're going to look for the point at this index. And this is actually pretty easy to write. I'm going to introduce a little helper variable here, which is just a spline coordinate space. Just because most of the functions that we're going to be using are going to need one of these, so we might as well just grab it. It's going to be spline coordinate space local, and then we're going to return fSpline point, and our constructor takes a bunch of arguments. The first argument that our constructor takes is actually this float that I'm going to worry about later. Specifically right now, I'm just going to pass in 0 for what's called the input key. And we'll dig into that in a moment, what that is and what we should be using instead of 0 and how we're going to provide that. Next, we just need to query the spline for a bunch of information about the point at this index. So the position is going to be spline get location at spline point index. And we need to pass in the coordinate space that we want that in too, which is just local. We can keep going. We need the tangents that are at those spline points. There's an arrive tangent and a leave tangent, which describes kind of like the shape of the curve at that point. So we're going to grab those two. We're going to get arrive tangent at spline point index C. And we're going to get the leave tangent at spline point index C. And then we need our rotation. And I'm just like eyeballing the documentation while I write this. Get rotation at spline point index C. And then get scale lastly. And then for this one, we don't actually need C because the coordinate system doesn't actually matter. So there we go. We've extracted the point at a given index just by grabbing all the pieces of it and kind of sticking it back together manually. So just as a test, let's just create a spline. Let's just offset this a little bit. We won't worry about the poles, like the supports on either side. We won't worry about adding the extra spline points. We're just going to offset this one. So let's do that by looping through all of the points in the source and just adding them to the dest using this function. And before we do that, though, we need to talk about this input key thing. So it just so happens that generally, as you're adding points to your spline, you just need this to be an incrementing integer. Like you want the first one to be 0, the next one should be 1, the next one should be 2, etc. So I'm just going to write a little helper function for adding these to our destination spline in a way that we don't have to worry about that. I just want this to be taken care of. So I'm going to write a little lambda, and it's just going to be called add point. And it's going to capture the destination spline. It's also going to have a little counter initialized to 0. And it's going to take in an f-spline point. And it's going to be mutable because we're going to need to modify the key as we go. And you need the mutable keyword in order to modify captures and lambdas. So the point, we're going to set the input key to just be key plus plus. So the first one's going to be 0, and then the rest are just going to be incremented by 1 each time. Actually, just to be good citizens, we're going to explicitly cast that. And then we can just do dest add point. There's actually an extra parameter to add point, which is this bool update spline, and it defaults to true. I'm actually going to pass in false for that. So what that parameter does is it just goes through and it recomputes a bunch of metadata about the spline. It like crunches a bunch of numbers to figure out all this information about the spline. And we don't really need to do that every time we add a point. In fact, it's pretty wasteful to do so. It's best just to do it once at the very end. So as we're adding all of these intermediate points, I'm just going to say that's false. But we do need to do it once before we return. Now I could just do this. I could just do update spline. And that would work, but that's not very robust. As a good C++ programmer, I know that anyone could come in at any time and add an early return. I mean, I have some right here, some early returns. Exceptions can get thrown. I want it to be ironclad that no matter how I exit this function, this gets called. I don't want to leave that up to chance. So I'm going to use a tool that Unreal provides and is also a fairly common pattern in the C++ world. There's this macro on scope exit, and the syntax is a little interesting, but you pass in, or you just follow it with some curly braces, and in there you put some code, and no matter what happens when this scope that we're in is exited, whether that's through an exception or through an early return or a regular return or whatever, this code will run. So having that in the on scope exit means no matter what, we will not leave this function without updating the spline. All right. it's time. So let's loop through the source spline component. Let's extract each point, and then let's offset the position of that point, and then add it to the dest, and we'll see what happens. So we're going to do a little for loop. We're going to do I is 0. I is not, I don't need to be narrating this out loud, I'm sure. We already have the count as a local variable. And then we're going to grab the point. We're going to extract it, rather, from the source spline, and the index is going to be I. And then it's actually not const, because we're going to modify the position. We're going to say point dot position, add our offset to it, and then we're going to add that point to our destination. So let's go ahead and build this and see what happens. While it's building, I just want to point out that, as you can see, we're not doing anything absolutely mind-melting here. All of this stuff would totally be possible in blueprints. I just find it a little bit easier to write this kind of code in C++. And in a bit, we're going to make it just slightly more complicated in a way that I'm even more thankful to be in C++. But nothing in here is fundamentally impossible in blueprints. In fact, all of these things are, if we go look, they're blueprint callable. Or if we go to the declarations, yeah, they're all blueprint callable, and so you can use them from wherever you want. So back in the editor, you can see nothing has changed, which makes a lot of sense because we haven't actually called that function we just wrote from anywhere. So I'm going to refactor this a little bit and make that happen. I'm going to add a pin 3, and I'm going to have all this stuff happen on step 3 because I have a step 2 that I want to take care of first. I'm just going to move all this kind of down and out of the way. And for step 2, I want to, where did our helper spline go? I'll just add that back in. I don't know where that went. I want to call our function and offset the helper spline a little bit. So let's do that. Let's do create offsetted spline. There it is. And our target is self. Our destination spline is our helper spline. Oh, you know what? We should probably make this static so that that self pin goes away. We don't actually need that. I'll deal with that in a second. Our helper spline is the dest. The source is going to be our regular spline. And just move these down a little bit more because I'm going to split this offset pin so that we can just hard code a value for now, and then we'll turn it into a nice parameter. But for our Z, I'll zoom in a little more. Our Z is going to be, let's say, 100. So that'll be like the height of our railing. And it actually didn't work because self, yeah, we do need to do this right now, actually. So 1 second. Yeah, so this function should be static. It should have been static in the first place because we don't need an instance of our function library. So we're going to rebuild. All right, so back in the editor, just to be safe, I'm going to break these links, and I'm going to refresh this pin, or this node, sorry. And you see the target self thing disappeared, which is good. That's what we wanted. And I'll drag this stuff back in. So our helper spline is the destination. Our regular spline is the source, and our offset Z is that. And then here, I'm going to make sure to swap this out for our helper spline. Our spline, our regular spline, is now just there to help the user describe the shape of the curve, but we want the actual spline that we trace for our railing to be the helper spline. So we'll see if that worked. All right, look at that. So we got our railing kind of suspended in midair above. Here's our spline that I can drag around, and you can see that it has an effect on this other spline that's actually being used to sweep the polygon. So now I should probably expose that offset value as a parameter instead of just hard coding 100. So I'm going to promote this to a variable, and we'll name it height. That'll go in there, and we'll make it public so that our user can now just kind of drag it around and adjust the height of their railing. I want to point something out just for completeness before we go on, which is that we haven't actually done anything yet that we couldn't have just done with this append sweep polygon node. So this thing has this transform pin, which you can pass in, and it will take all of these transforms in the sweep path, and it will transform them one more time by this before it actually generates the mesh and adds it to the target mesh. So if we only wanted to do this, we absolutely would have not needed to go into C++ and stuff and do all this. We could have just passed in a transform that described that Z offset and called it a day. The reason that we've done it the way that we've done it is because we're going to do more in C++ in a moment. So please don't take this as my advice that you have to do all this in order to just offset a spline a little bit. It's only because of what we're about to do that I wanted to set up that infrastructure. All right, so before we go on, I just thought of a small improvement we could make to this function, so let's take a look. You remember how I said that we only need to update the spline once at the very end, and we added this scope exit thing to do that for us? Well, we're actually still updating the spline twice throughout the course of this function. We're doing it once up here when we clear spline points. Now, this function actually takes that same bool parameter, update spline, and it defaults to true. So right now we are passing in true right here that yes, we should update the spline when we clear it. Now that's probably not the hugest deal. I'm sure that it's very fast to update to a cleared spline, but if we could do better, we might as well just do better. So I'm going to pass in false here first of all. So we're not going to update the spline when we clear it, but we do still need to update it once when we leave. And now we could leave one of these places instead of just down at the bottom. So I'm going to drag this on scope exit up above the clear spline points. And now you can actually see the power of this on scope exit thing. We no longer know clearly which return we're going to take. We could take one of the early returns, we could take the last return, and regardless, this code's going to run and make sure that we update our spline. I could have put this after the clear. The reason I don't want to do that is just for future proofing, making sure this code doesn't develop bugs in the future. If I put them in this order, it's pretty easy to accidentally come in and add another return in between, and suddenly I've short-circuited this from happening. Whereas if I just put it before, it's way harder to accidentally make that mistake. If I come in here and return dest, whatever, that's fine. I didn't introduce a bug in between the two lines that I care about. All right, so let's finally see how to add some legs to this thing. So we have these two splines. One of them's down on the floor as kind of a guide for our designer or our user of our script to author the shape of the railing. And then the one that's suspended in midair is a separate spline that we created that's offsetted up so that we can trace out some geometry. And as I've been saying, for the legs, we're actually going to add some points to this upper spline. And the first thing we need to do is add some points that connect with the ground on either side. I'm just going to start with one side though, just to simplify things. So I actually see a point right here down on the floor as part of our authoring spline that would be really nice to just be able to add this and have it kind of shoot up and connect with this upper spline and give us the leg that we need right there. So let's go over to our C++ and see what it looks like just to add this point to our spline. So in our C++ code, we have this loop that copies over all of the points from one spline to another. Before we do that loop, I'm just going to add a point right before that is a copy of the first point on our origin spline. Not offset it at all, just so that it's sitting on the floor like we want it to be. I'm actually just going to put this in a little inner scope, and that's just going to help us out later. And so the first point is going to be, we're going to extract the first point on our source spline. And let's just see what it looks like if we add that point to our spline. So we're going to add the first point unmodified to our destination spline. And then we're going to loop over and add all of the offsetted points. So let's see what that looks like. So back in the editor, you might not see anything has changed. And that's just because we need to give the script a little poke so that it runs again. So I'm just going to drag this control point. Whoops. Okay, so you can see what we did. We added a point down here, which is nice. But it doesn't exactly look great. If you look closely, you can see that our spline is doing like this S shape in here, and our mesh is all messed up, but we can maybe fix that after we deal with the pressing issue of our spline being wrong. So we really want the spline to just go straight up right here instead of snaking around like this. And the reason that it's doing that is we've just copied the point up here, or sorry, the point that was already right here. This point is going off in this direction. And so we're saying, hey, spline, start heading in this direction and then meet up with this point way up here that's heading in the same direction. And so it's kind of jutting out, and then it kind of has to double back on itself so that it can meet up at that point with a continuous curve. So we need to not just copy the position of this point. We need to actually flip it so that it's pointing upward. So let's see how we do that. Okay, so we are going to take our point, and we need to adjust the rotation of it and also the tangent of it. And that will help us point it in the direction we want it to. So first of all, what's the direction we want to point it in? Well, conveniently, we already have the direction that we are offsetting things by in the form of this vector right here, offset. And so we're just going to use that directly. And so the rotation of our point is going to be offset rotation. And then our arrive tangent and our leave tangent, which are the two ways that we can control our tangent in our f-spline point struct, those both need to be set to the same value, and it's going to be the same rotation. So let's see how that looks. Our arrive tangent, I'm just going to string these together for style points, and that's going to be offset. And now let's see how that looks. All right, so back in the editor, I'm just going to give this control point a little tug again. And look at that. So our point is now the correct orientation. It looks like it would hit the ground if our railing was flush with the ground, which it's not right now. It's floating up in the air a little bit. And so that looks nice. This up here does not look so nice, however. So we figured out how to get this thing moving in the right direction. We're going to need to do some similar work up at this top kind of shoulder. And so let's zoom in and look at that. So we have this point that is directly above this other point. And what I want this spline to do, it's jutting out right now because of the tangent and the rotation of this thing. I would like a pole to go perfectly straight up until maybe like right about here. And we'll give the user a curve radius parameter, of course. But at this point, it's going to start curving around, and it's going to meet up with this spline maybe about here. And so my plan for this is to actually take this point and split it into two different points, one of them right below and one of them just to the right. And those 2 points are going to form the kind of bend. And to be clear, this point right here is not going to be in the spline anymore. I'm going to split it into two. So let's start with the one below because it's just a little bit easier, and then we'll talk about the one to the right. All right, so I'm going to be adding a couple more points to this inner scope right here. And first thing I'm going to do, I'm just going to rename this one so it's more descriptive. This is going to be called floor. And that's going to be the one on the floor, as we already saw. Now we're going to create this point that's up a bit, and it's just below the shoulder that we're going to try to create. And so we're actually going to be able to use this same point to start with, but we're going to have to make some little tweaks to the position of it. So I'm going to call this loop cut, which might not be the most intuitive name, but I'm using that term. I'm thinking about like in Blender, when you do a loop cut near a corner, it helps give that corner some tightness. And that's pretty much exactly what we're doing here. So I figured it's a fitting name. So we're going to start just by copying the point we already have. And then we need to move it up a little bit, but not all the way up to our offset. we're going to move it up in the offset direction, but we're going to shave off a little bit. So the way that that's going to work, we're going to have to define a parameter. I'll expose this as a proper parameter to this function in a little bit. But for now, this is just going to be corner radius. And I'm going to just say like 10. And so the position of our loop cut is going to be the position on the floor plus the offset with a little bit shaved off. And so what does that look like? So in order to shave corner radius units off of the offset, first we need to know the magnitude of the offset. The magnitude or the length. And whatever this is, that's kind of our baseline. We're going to subtract some corner radius off of it, and then we're going to multiply offset normalized by that to basically change what the length of offset is, but not change the direction of it. So our loop cut magnitude is going to be the offset magnitude minus the corner radius. And then our actual loop cut offset is going to be our offset times loop cut magnitude divided by offset magnitude. So we're kind of removing the fact that it used to be this long, and we're adding in the fact that it's now this long. So this basically just sets the magnitude of offset to be this. And so now let's use that to adjust the position of our loop cut. And let's see what that looks like back in the editor. Actually realized that I forgot to add the loop cut. Now let's go back to the editor. All right, now giving the spline the customary little nudge. All right, so this mesh looks terrible, but if you look closely at the spline, you can see we have a point and then a straightaway, which is nice, that's what we want, and then another point just below the start of the real spline. And that's 10 units below. That's controlled by our corner radius that I'll expose as a parameter before we're done, I promise. And so now let's talk about how to move this point over a little bit, because we want to offset it so that the elbow between them is the curve that our mesh is going to take. So if you think about how to do this, it's like we need to nudge this point over a little bit along the spline. So we already have the spline, so we know which direction it should go, but we just want to say like, hey, bump yourself over a little bit by the corner radius. And then that'll give us this nice kind of triangle right here. So we need to have some way of saying like, hey, give me a point along the spline that's like corner radius units down the spline. And luckily, the spline component gives us an API to do exactly that. So we need to figure out a way to sample a point that's a little ways along our spline. So we already have this function called extract point at index, and it uses all these APIs, get location at spline point, get tangent at spline point, blah, blah, blah. There are also APIs in the useSpline component class, I'll just show you right here, called things like get location at time and get location at distance along spline. You can also use that input key thing that I talked about. And we are going to want this one. We're going to want to get a location and a rotation and all that stuff at a distance along the spline. And the distance along the spline is going to be the corner radius. And if we stick all those pieces of information together, we're going to get that point that's partway along the spline like we need. So I'm just going to start by actually copy pasting this function and renaming it. And we're not going to pass in an index anymore. We're going to pass in a distance. And so now we're going to build up our spline point in the same way, but instead of these at spline point functions, we're going to be calling at distance along spline, and we still need this coordinate space parameter. So we're just going to keep going through. Now for our tangents, there's an interesting issue here where there actually is not an API called get arrive tangent at distance along spline. There's an arrive tangent at spline point, but for an arbitrary spot on the spline, there's really only one tangent in general at any given point. And so we're just going to use the same tangent for both of these. And so we're going to just save it in a local variable so we don't have to compute it twice. But it's going to be a float. We'll call it tangent. And it's going to be spline get tangent at distance along spline. And we can just replace both of these with that. All right, now I'm just going to fix these last two. And what's it complaining about here? Oh, yeah. My mistake. This is an F vector. All right. So now we have a point at a distance along the spline instead of an index in the spline. So let's use that to create our third point that we need. And I'm going to name this point curve start. And it's going to be extract point at index, or sorry, not at index, at distance along spline. And the distance is going to be, or we need to pass in the spline. And then the distance is going to be the corner radius. And we're going to add this to our spline. And we also need to offset it up so that it's up top with the rest of the points that are on the spline. So we're going to take the position and we're just going to add the offset to it. And let's see what that looks like. All right, you can see that our point ended up where we want it to, but we forgot to remove the middle point. So let's do that real quick. So down here in our loop, we're actually not going to start at 0 anymore. We're going to start at 1, and that should do the trick, actually. All right, so moment of truth. There we go. So we have split our 1 point into 2 points. You can see that we're doing a little curly Q here, though. And the reason for that is that the magnitude of our tangents on these points is way too big. So we're actually jutting out way too far, and then we're looping back around and correcting. So we need to shorten that so that we just get that like nice round shoulder that we're looking for. And so we're going to do a little bit of math to do that. It's not too hard. Okay, so we're going to do a very similar trick for setting the magnitude of the tangents as we did right here, where we kind of divide out the current length and we add in, or we multiply by our new length that we want. So the length of our tangent, which actually I'm just realizing we forgot to even set for our, or no, we don't need it for the loop cut because it was already pointing up, but we do want to modify the magnitude of it. So we're going to take that and we're going to say that the leave tangent, we're going to multiply the leave tangent, which essentially changes the magnitude of it, by 2 times the corner radius. The 2 just makes sure that we kind of follow through the entire curve, and it just ends up giving the curve like a nice rounder look. You can take my word for that, or you can test it either way. And I think you'll find that the 2 is what we want. So 2 times the corner radius divided by the old length. And then we're going to do the same thing for this curve start point, except we're going to modify the arrive tangent magnitude. So it's 2 times the corner radius divided by the old arrive tangent length. So let's build and see what that looks like. All right, so adjusting a little point. So our script reruns, look at that. We got our nice little elbow right there. And that's just due to the fact that we have 2 points and they are in the shape that we want. And our spline is just kind of automatically drawn in between them. And they have the right directions and the right magnitudes. So we get that nice little shoulder. So that looks pretty good for that side. We still need it on the other side, and I'm just going to do that. It's very similar to doing it on the first side. You just do a couple things in reverse. So I'm not going to talk too much through that, but I will just do that so you can see it. All right, so there it is. It's working. So basically what I did is the first thing is I pulled the add points out and factored them out to the very end here. So that way I could just copy paste this whole block down here and then change the order of them so that they are defined in kind of a parallel order, but we have to add them in reverse order because we're at the end of the spline. So we need to add like the curve end first and then the floor last. So then I just flipped some stuff around, changed the sign of the offset, changed some arrives and leaves, and that's about it. And then I, in order to get the last point, I'm looking at the very end of the spline and I'm subtracting off the corner radius and sampling a point right there. So that's how we get that end corner right there. So now I'm going to expose the corner radius as a parameter, as I've been saying I would. So that's just going to be a float corner radius. Got to add that to the header file as well. And we will build. All right, so over in our railing, now when we create our offsetted spline, I'm going to refresh this node. You see we have this corner radius parameter, and I'm going to change that to 10 because that's the hard-coded value we had, but I'm also just going to expose it as a variable. So promote to variable, and that's a perfect name for it, and I'll make it public so we can edit it on our instance. And now if we drag that number around, we can see the corners getting more and less bendy. That's kind of a cool effect on its own. Now I think this is pretty much ready to say that we're done. I do want to talk about one final little thing that was kind of a head scratcher for me, which is that let's actually just go a little crazy for a second and let's twist this around a little bit. And you can see that our corner that we just spent all that time making looks pretty bad when we do that. You can see that it's kind of twisting around itself. And the reason for that is because we weren't very careful when we set the rotation of our points right here. We don't want them just to be going up. We want them to be going up in a way that's going to then meet up with this curve nicely. So back in our C++, we need to change the rotation that we're using for the floor right here. Now I'm going to use a little sneaky fact, which is the fact that we have just copied the point out at 0, at index 0 on our source spline, and we haven't modified it yet by the time we get to this line. So the tangent on it is going to be equal to the tangent of the start of the railing, and that's exactly the tangent we want to match here. So we're not only going to set our floor's rotation to the offset's rotation, but we also want to add in the existing floor arrive tangent rotation. And that's going to make it so that those match up nicely. And again, I'm only using floor right here because I know that I haven't actually modified the arrive tangent yet. If I did this a couple lines later, it wouldn't work. You might argue that this is a little bit too sneaky, but it's the simplest way to do it for now. And I'm going to do the same thing on these. So we're not just going to use this negative offset. We're also going to use the leave tangent of our last point, which again is still floor by this point because we just copied it. All right, so if we force the script to run again, there we go. So our gross twisty corner is now nice and smooth because this is sensitive to which angle of up it needs to be using in order to join up with the railing nicely. So you can keep iterating on this. In the beginning video, I know I had like this horizontal bar that was sticking out. I'm actually, sorry for the bait and switch, but I'm actually going to leave that as an exercise for the viewer. It doesn't do anything that we haven't already done yet. So if you've understood everything that we've done so far, that should be pretty easy to do. You can add materials to this. You can add more parameters. And I just thought that this was a really interesting exploration of some geometry script tools, some math, and some cool ways that you can programmatically alter splines after they've been authored in the editor. One more thing that I want to do before we go, this has actually gotten a little bit harder to use. So I can actually go in and select points on our helper spline. And if I try to drag them around, they get this weird glitchy thing happening. And the reason for that is that when I drag them, it triggers our script to rerun, which sets them back to where they were. So there's no real way I can move them around. And even worse, I can accidentally select them. It's not happening right now, but if I'm tapping around the base and I'm trying to move these points at the end, I could accidentally select the helper spline points, which would be really annoying if I was trying to modify this thing and I kept accidentally selecting the wrong thing. So I'm just going to do one more thing, and that is at the end of my script, I'm going to delete our helper spline component. Now, I don't think that this is going to be in any like best practices book. I do think this is a little bit of an anti-pattern for how you're supposed to use components in Unreal. You're not really supposed to just like create them and destroy them constantly. They're not really supposed to be scratch space for computations, but I couldn't really find a simpler way of just creating a temporary spline and then destroying it at the end of our script, aside from adding it as an actual component on the actor. So we're going to do that. We're just going to leave it there. But at the end, I'm going to make sure to destroy a component, and that's going to be the helper spline. So that's going to be our last step. And now this means that actually at the beginning, we're going to need to make sure to create one if we don't have one. So I'm going to ask, is valid on our helper spline? And if it's not, I'm going to create, or I'm going to add a component by class, and the class is going to be uSpline component. And then I'm going to set that return value to be the helper spline. So if I compile that, now you can see that our helper spline is not even here anymore. And that's because it only exists while our script is running, but we can still modify the original spline, and the helper spline doesn't get in our way anymore. Now, if we wanted to debug it, I mean, it was pretty useful to be able to visualize it while we were working on it. You could just go back in and not destroy it anymore at the end of the script. And then this would only take effect if you had destroyed it. But that's just like a little usability tweak that I found to be pretty cool when I was working on this. So I think I'm going to call it there. I really appreciate people sticking around this long. And we got an interesting little kink right there, but that's just because our curve was kind of twisted in that spot. So yeah, I think that about does it. But thanks for watching, and see you later.